Hi, and welcome to Week 9 Mini Lecture 1 for the Quantum Universe for Educators. In this lecture, we're going to go over another sample calculation for the probabilities of the various outcomes of a Stern-Gerlach type measurement. And the calculation is going to be similar to the one we did last week, but we're going to use a different starting quantum state, and we're going to use matrix notation instead of the bracket notation that we used last week. Okay, so just like in the previous example, we're going to imagine our set of silver atoms are described by this particular quantum state here. The quantum state we're using this week is given by psi, which is equal to the plus ket in the z direction plus e to the I pi divided by 3 times the minus ket in the z direction. This will allow us to see how we deal with complex exponential factors in our quantum states. These factors of e to the I something are usually called phase factors in quantum mechanics. Now, in matrix notation, the plus and minus basis kets are just described by column vectors, with the plus state being described by 1, 0 column vector and the minus state by 0, 1. So when we combine them together in this combination, what we get is that the state psi is described by the column vector 1 e to the I pi divided by 3. Okay, so we first have to, just like last time, go through the process where we figure out whether our state is normalized, and if it isn't, we have to normalize it. As a reminder, a vector is normalized if its inner product with itself is equal to 1. In other words, its magnitude squared is equal to 1. Okay, so in this case, in matrix notation, the inner product of a state with itself is the bra version of the state times the ket version. To obtain the bra version of the state in matrix notation, you take the ket version, which is a column vector, you turn it into a row vector, which is an operation called transposition. We take the transpose of the column vector. All that means is we turn every column into a row and vice versa. And we also take the complex conjugate of the elements of the column vector when we place them in the row vector. So the complex conjugate of e to the I pi over 3 is e to the minus I pi over 3. Again, we just stick a minus sign in front of the imaginary number I. And then the inner product is just the row vector here times the column vector here. So to calculate that, we take the first element of the first row times the first element of the first column, that's 1 times 1, and add it to the second element of the first row times the second element of the first column. So that's e to the minus I pi over 3 times e to the I pi over 3. This first term is clearly just equal to 1. The second term, well, if we multiply together two things with exponents, then the exponents just add together. So we have e to the minus I pi over 3 plus I pi over 3, which is equal to e to the 0, and e to the 0 is equal to 1. Anything raised to the power 0 is equal to 1. So the inner product of the state with itself is equal to 2. So it's not normalized, but again, as we covered last week, we can normalize the state by dividing by the square root of whatever we get here. So the square root of 2. So the state, the quantum state that we use is given by psi is 1 over root 2 times the column vector 1 e to the I pi over 3. Now this week we're not going to calculate the probabilities of measuring the spin along both the x, y, and z directions like we did last time. I'll just concentrate on the y direction. So as a reminder, once again, the probability of measuring the spin along the y direction to be up, to be plus h bar over 2, is equal to the inner product of the plus state along the y direction with psi all squared. And similarly for the probability of measuring the spin down along the y direction. So in order to calculate this, we need to look at what the plus and minus kets along the y direction are. So last week we saw that they can be written in terms of the plus and minus kets along the z direction in this manner here. And now we want to use this to obtain the plus and minus kets in the y direction in matrix notation. To do that, we again use the fact that the plus and minus kets in the z direction are just the column vectors 1, 0 and 0, 1, which means the plus and minus kets in the y direction are given by these two sums here, which add up to the following column vectors. So the plus ket in the y direction is equal to 1 over root 2 times the column vector 1i, and the down ket in the y direction is equal to 1 over root 2 times the column vector 1 minus I. Now, in order to form these inner products, we have to figure out the bra versions of these states. And again, remember, in matrix notation, the bra version of a state is given by turning the columns into rows and taking the complex conjugate of any complex components. So the up bra in the y direction is 1 over root 2 into 1 minus I, and the down bra in the y direction is 1 over root 2 1i, where I emphasize here that we've taken the complex conjugate of the imaginary number, which is the bottom element in the plus y ket, and is minus I in the down y ket. Okay, so the inner product of the up y ket with psi we can now calculate, and it's given by the following. It's 1 over root 2 times 1 over root 2, these are the factors, the constant factors outside these states, times the row vector 1 minus I times the column vector 1 e to the I pi over 3. So again, the first element in the row multiplies the first element in the column, the second element in the row multiplies the second element in the column, and we get that this inner product is a half into 1 minus I e to the I pi over 3. And the probability of measuring spin up along the y direction is just this inner product squared. Well, the square modulus of a complex number, remember, is just the complex conjugate of the number times the number itself. So we get a half times the complex conjugate of 1 minus I e to the I pi over 3, that's denoted by the star here, times 1 minus I e to the I pi over 3. To take the complex conjugate of this complex number here, again we just reverse the sign in front of the imaginary number I, right? So the minus sign here becomes a plus sign, and in the exponent we get a minus sign in front of the I pi over 3. So we can then just multiply out these two brackets here, and we get 1/4 1 minus I e to the I pi over 3 plus I e to the minus I pi over 3 minus I times I e to the minus I pi over 3 plus I pi over 3. I times I is minus 1, since I is just the square root of minus 1. So, and the exponents add to 0, and e to the power 0 is 1. So this last term here just reduces to plus 1. And so we end up with this answer for the probability that the spin is up along the y direction. It's 1/4 into 2 minus I e to the I pi over 3 plus I e to the minus I pi over 3. So to go any further, we need to figure out what this combination of these two exponentials is. So to do this, we're going to need to use Euler's formula, that e to the I theta, where theta is whatever the factor is in the exponent, is equal to cosine theta plus I sine theta. So in this case, we have e to the I pi over 3, which is equal to cosine pi over 3 plus I sine pi over 3. And we have e to the minus I pi over 3, which is equal to cosine pi over 3 minus I sine pi over 3. So these are the factors we're going to use in our expression for the probability, which contain both of these factors here. So let's go ahead and substitute those factors in. So the probability of spin up along the y direction is 1/4 into 2 minus I times the cosine plus I sine combination plus I times the cosine minus I sine combination of factors. And so we can multiply these factors of minus I and plus I into these brackets here, and bearing in mind that when I is multiplied by I, we get minus 1. So we get this combination here, that the probability is 1/4 into 2 minus I cosine pi over 3 plus sine pi over 3 plus I cosine pi over 3 plus sine pi over 3. Notice that the cosine factors actually cancel and the sine factors add together, and so we end up with the result that the probability is equal to 1/4 into 2 plus 2 sine pi over 3. Sine of pi over 3 is square root of 3 over 2, so our final result is that this probability is 1/4 into 2 plus root 3. Plugging that into the calculator, we get 0.93, which we can add up here. So that's a 93% probability of measuring spin up along the y direction. Okay, we repeat this procedure for the spin down along the y direction. And notice that the only difference in our calculation is that in this inner product here, the row vector is 1i, whereas before, when we had the plus vector in the y direction, the row vector was 1 minus I. So that we're only going to differ here by a minus sign. So we can again multiply together the row vector with the column vector, and we get the result that this inner product is a half into 1 plus I e to the I pi over 3. The probability is the modulus of that squared again, taking the complex conjugate of 1 plus I e to the I pi over 3 gives us 1 minus I e to the minus I pi over 3. Multiplying out the brackets here, and noting that in the last term, once again, I times I is minus 1, and the exponents add up to 0, and e to the 0 is equal to 1. So we end up with the result that the probability of spin down along the y direction is equal to 1 quarter into 2 plus I e to the I pi over 3 minus I e to the minus I pi over 3. Once again, we have to use Euler's identities here. We substitute in these expressions for the complex exponentials in terms of cosines and sines. We get this expression here, multiplying the factors of I into these parentheses, and bearing in mind again that I times I is minus 1. Then once again we can see that the cosines cancel and the sines add together. The difference with the previous probability is that the two sine terms are negative rather than positive, so we end up with the probability of spin down along the y direction is 1 quarter into 2 minus 2 sine pi over 3. Apologies, this here is meant to read spin down in the y direction. This is meant to be a negative here. So this is a quarter into 2 minus 2 root 3 over 2, which is a quarter into 2 minus root 3. Plugging that into your calculator, you'll find that it is 0.07. And so the probability of measuring spin down in the y direction is 0.07. That's a 7% probability. And finally, let's do our usual check. Do the probabilities add up to 1? Yes, they do. So it looks as though we've managed to carry this out without making a mistake.